Ladies and gentlemen, I think we can get started. If you please take your seats. Thank you. Our next speaker for today, Dr. Jianhui Wang, is a world-renowned researcher in power system operations and control and in grid resiliency and cybersecurity. It's a privilege again to introduce him today. He holds the Mary and Richard Templeton Centennial Chair Professorship at the Department of Electrical and Computer Engineering at Southern Methodist University. He obtained the PhD from Illinois Institute of Technology, Chicago, US in 2007, and worked at Argonne National Lab from 2008 till 2017 before joining the academia. Dr. Wang is the principal investigator on a multitude of energy-related research projects focused on smart grid applications, renewable integration, grid resiliency, and cybersecurity, as I mentioned before. Dr. Wang is the past chair of the IEEE Power and Energy Society Power System Operations, Planning and Economics Committee. He is also the recipient of the IEEE Chicago Section 2012 Outstanding Young Engineer Award. Dr. Wang has authored and co-authored more than 500 journal and conference publications, which have been cited more than 50,000 times with an H index of 119. He is an associate editor of Journal of Energy Engineering and editorial board member of Applied Energy and IEEE Power and Energy magazine. Dr. Wang is the past editor-in-chief of IEEE Transaction on Smart Grid from 2015 to 2019, and an IEEE PES Distinguished Lecturer. He is also a guest editor of Proceedings of the IEEE Special Issue on Power Grid Resilience. He is the recipient of the IEEE PES Power System Operation Committee Prize Paper Award in 2015. Also the 2018 Premium Award for Best Paper in IET Cyber Physical Systems, Theory and Applications. The Best Paper Award in IEEE Transactions on Power Systems in 2020, the IEEE PESP SOPE Committee Prize Paper Award in 2021, and the IEEE Transaction on Power Systems Outstanding Paper Award in 2023. Please welcome Dr. Wang. Sir, the floor is all yours. Thank you.
Thank you so much. I should have sent you a shorter bell, so you don't need to write that long. Thank you for. Should I load the slide?
Okay, I already.
Oh, okay. So thank you for being here, and thank you for coming back. Again, my name is Jianhui Wang. I used to work at this Argonne National Lab, which is the DOE National Lab in Chicago. I moved to academia in 2017. Today, my topic is about I click? Okay. Thank you. Okay, so my topic is about this integration of hydrogen into energy system. I'm going to look at three different aspects here. One is reliability assessment and optimal operation and planning. So my background is power system operation, and I knew nothing about hydrogen about 2 years ago. So in the past 2 years, I've been learning hydrogen myself. So this is some recent work that we have done in this area. So this is a kind of outline of my work. So one of the topic is a reliability assessment of integrated energy system considering hydrogen. So the idea behind this topic is that so if you integrate a lot of hydrogen into the energy system that we already have, we have power, we have gas, and we have heat, right? We already have a very complex energy system. Now you are integrating another kind of source of energy, hydrogen, either coming from coal, either coming from green energy, into the already complex energy system. So what's the impact of that? So what's the impact of integrating hydrogen on power system reliability? So that's the angle of the first topic. The second topic is optimal operation of integrated energy system with hydrogen integration. The third topic is about planning, so how you can optimally plan such a system. So this is some background of my topic. So as you all know, if you are in the PhD thesis defense this morning, you know a lot, already about how important hydrogen is and how we can integrate the hydrogen into the markets, into the energy system operation. So you have learned some of that. So, and hydrogen is very promising technology. And if you go to any major conferences, and if you read headlines from newspaper, you will see that hydrogen is really kind of a game changer. For many industries, for many countries. I did some of the kind of Google search last night. I found out that Canada is actually one of the top producers of hydrogen in the world. So you are in a good spot here. So hydrogen is very kind of advancing quickly. And so there, every time I go to major conferences, people talk about this hydrogen all the time. I'm also leading this HB task force on hydrogen myself. So I talked to some colleagues from Europe, from Australia, from China. They are all doing hydrogen big time. So one person from Europe was saying that, telling me, is that they are building this intercontinental hydrogen pipeline. So that's quite large if we are thinking about that, right? So hydrogen is very kind of ambitious goal that people have in their mind. So this is from this IEA report. So the total hydrogen demand is projected to increase to 528 million tons in 2050. So and also, so you can see this very big goal. And also people are saying that the hydrogen, the main idea between the hydrogen is that, so we had some of the discussion in the morning. So, and then we have a question from the audience saying that if you can use hydrogen, if you can use renewable such as wind and solar to power the grid, why do we need to convert wind and solar to hydrogen, then to fuel cell, then to power demand, right? So the part of the reason of doing that is that we have too much renewable energy at certain points in time in our grid now. So there are a lot of times during the night, in some parts of the US, at least where I live, so they curtail wind power, they curtail solar power because they have too much. So which means that it's waste, right? So the idea behind this green hydrogen is that, so for some places where you don't have sufficient demand, you can convert wind and solar into hydrogen. Then the better part of hydrogen is that they can be transported. It can be put into this tank. You can store hydrogen for a long period of time. So that's another benefit of using hydrogen here, because it's long duration energy storage capability. So if you look at the battery, you look at the 4-hour battery, the capabilities. But if you look at the hydrogen you put in the tank, you're talking about this cross-seasonal storage capability, which is much needed in some places in the grid. So which means that's all the benefits about hydrogen. So that's why people are kind of going after hydrogen in such a way. So that's the reason that people are using that. We are mostly talking about the green hydrogen here. There are different colors, right? There's gray, there's blue. I'm talking about green hydrogen, meaning that most of the hydrogen what I'm talking about here is produced with wind and solar. So renewable energy-based water electrolysis to produce hydrogen, we can mitigate this renewable energy curtailment and facilitate this net zero emission targets by 2050. and also another way of using hydrogen is that you can blend hydrogen into the existing gas pipelines. So we burn gas, to generate power. We burn gas to provide heat. So you can basically mingle hydrogen into natural gas pipeline. So you don't need to build another pipeline for hydrogen transportation. So which is another benefit of using hydrogen now. So but you can only go to a certain percentage of hydrogen in the pipeline. So right now the common goal is about 50%. You cannot really go beyond that. That's gonna incur a lot of other issues, compliance, safety, reliability. There's a whole host of issues that you need to deal with. But mostly people are talking about this 50% to 20%. So, and this is by 2050, so 62% hydrogen can come from electrolysis, and 30% hydrogen can be used for electricity production and fuels. So, so there are some ways that you can produce hydrogen now. So one is the dominant way is steam methane reforming SMR. So this is the major way of doing this. But if you do this with coal and gas, and it's not clean enough, so we don't like that. So another way, another is the green. This is the green electricity-based electrolysis, and also in terms of transmission, you can transport hydrogen in this tube trailer that they can just move hydrogen around, as you can see here, and also you can build a small-scale hydrogen pipeline. I don't think we have many large-scale hydrogen pipeline yet. Maybe in the future, But another feasible, more kind of efficient way of consuming hydrogen is to blend that hydrogen into a gas system that we already have. Also, hydrogen is being consumed by many industries in the world. Steel, agriculture. There's a lot of industries that can consume hydrogen directly without any conversion. So, and also the long-term goal is that we can do this SMR with CCS, carbon capture and sequestration, and we can have renewable-based electrolysis, which is still small now. And we can have a high-temperature electrolysis. The benefit of high-temperature electrolysis is that the efficiency of this technology is much better. So, and also we can have this large-scale hydrogen pipeline, and we have other more industries using hydrogen. Transportation, we have hydrogen cars, I'm sure you have seen the news, and then we have buildings, power generation. Okay, so then the question we can ask is that, so how do you model hydrogen in the gas pipeline, right? So we already have the gas pipeline, then you plug in another energy source, hydrogen. How should you model hydrogen flow in the pipeline? And what's the impact of doing that on power system reliability and the cost and all other metrics? And then how do you model the electrolyzer operation? So they can have multiple operation conditions, on, off, idle. So how do you model that? And what's the feasible region of that electrolyzer operation? So, and then those are the technical constraints. And also, and how you can model this hydrogen into this planning and operation of our integrated energy system. So the first topic we are looking into is the reliability assessment. So this is kind of the context that we are looking at here. So basically, we are saying that we can use renewable energy to generate to provide electricity for the electrolyzers to generate H2 hydrogen. The hydrogen can be put into a tank to store hydrogen for a period of time. It also can go to this methanation process to generate the synthetic natural gas. It also go directly into the natural gas system here. So for doing this, you can see that we can have the renewable generation as a source to generate the hydrogen and go to this natural gas system, either through methanation process here or just blend the hydrogen directly into the gas system here. So then the question we want to ask here, so if you do this, what's the overall reliability impact? And how is that going to affect my traditional power system reliability indices, like IOLE and all other indices? So this is kind of the technical formulation that we have. So basically, we are saying that you can model the hydrogen in some different ways. You can do this state equation, which is built on chemistry and physics, context. So you can see that this equation basically set up this relationship between the gas pressure, density, temperature, and other gas and pipeline related physical properties. So because you have two different gases in the pipeline, so it's all interrelated. And also those are the kind of physical properties of those gas flows. You have the average molecular weight and the compressibility factor. So the critical temperature is an important factor here. And the pressure of the gas is also very important here. So all of those equations is going to be affected by hydrogen fractures in the natural gas pipeline. So what I'm saying here is that, so if you increase the hydrogen by a certain percentage, 15, 20, 30, all those parameters of those equations are going to change. So that's going to affect your technical calculation. So and then there are several fundamental equations that you can use to model the gas flow. It doesn't show completely here. Oh, okay. I don't know what's going on. Okay, maybe something is lost during my PDF conversion process here. So, okay, in that case, so this is one of the equation is a continuity equation here. Basically, this means that you should have this principle of conservation, which is one of the fundamental equations for fluids, right? So you should have that continuity equation. So basically, and this is not easy equation to solve. So, but if we can define this gas flow rate, you can have this equation. Just imagine you have this equation. Even though that's shown here, sorry. And another equation is a momentum equation, which means that which kind of model all the forces that are being imposed on these gas particles. So this is another equation that normally associated with gas flows. So, and then this is the equation are not easy to solve either. As you can see, this is fairly complicated. So, and if we neglect this gravity effects and the inertia and the kinetic energy, so you have this simplified version of this equation. So those two equations are partial differential equations, which are not easily combined with MIP solver, right? With MIP formulation, and we don't even do that. So. So then we have this a more kind of simplified version of doing that. So we can discretize those partial differential equations with all those back difference method. So you can have this kind of equation, which are more easily solvable than compared with the partial differential equation. So let's become this our new continuity equation here. This will become our new momentum equation here. We also model this Lamp-Pack capability. Lamp-Pack capability means that because gas flows gas could be stored in the pipeline, so it does not disappear. Instantly. So you always have some gas stored in the pipeline. So you have this Lamp-Pack capability which provides certain storage capability. And this K1, K2 are coefficients related to the pipeline and the fractions of various natural gases. And so this Lamp-Pack capability is important as I show here. So for static gas flow, which is a simplified version compared with the dynamic gas flow in the last slide. So here we are seeing that if you drop the continuity equation and the Lamp-Pack, then you have this equation. And also, we assume that inflow equals to outflow. So then the momentum equation is also here. So here we just ignore the dynamic flow of the gas. We assume that is constant in a steady state condition. So basically, it's an even further simplified equation that we have here. So which is easier to calculate, but it's a simplification that we are making here. So the remark here are that the steady gas flow can provide as a base point, as a base case, as a reference point. So we're going to compare the dynamic gas flow with this benchmark. And also, we're going to inject this hydrogen into a natural gas system to see how is that going to affect both the steady state and the dynamic gas flow here. And also, the momentum equation can be linearized using piecewise linearization and second order Kohn programming here. It's all lost. Okay. Sorry. So this is the equation that I have. So I just want to tell you that. So this is the cost of the shed load. Also, we have this generation cost here. We also have the gas load here. Gas load here, if you shed the gas load, you are also going to incur a penalty of doing that. So this is trying to minimize the amount of power, gas load, and renewable energy curtailment. So we want to minimize that. And also, we have all the technical constraints here. We have the power to hydrogen constraint, power to methane constraint here. So, and we have all the typical constraints here. Power box and natural gas system. Okay, so those are the reliability indices that we are going to use. So some of those they are already used in the energy system. LYP, loss load probability, and expected load not supply. Those are the commonly used indices that we use in our energy system reliability analysis. For the natural gas system, we have something similar. We have loss of gas probability and expected gas not supply. For the wind farm, because we are also looking at how we can minimize renewable energy curtailment, we have loss of the renewable energy probability and the expected renewable energy not supplied here. This is the flowchart that we are trying to use. So basically, you have 1 year, we have 52 weeks. You break that 1 year into 52 weeks, and for each week, we run this steady flow model first, because that can be served as a starting point, because that's the fastest way to solve that problem. Now, then you solve more detailed model using the dynamic model. Then after you're done with 1 week, you go to next week. Now, in the end, if the variance of energy shared it does not change very much, you stop. So this is the flow chart. So after you're doing this loop, you can calculate all the reliability indices shown in the last slide. So we have this HB24 bus case here. And here we also couple this power system case with this 20 node natural gas system here. So this is a power system case, and they are coupled, as you can see. So this is the power system, this is natural gas system. This is all made up, so we don't have any real system. So that's something that we have now for now. So for the power system, we have 38 transmission lines, 22 conventional generators, and 3 wind farms. And the wind farms are buses 21, 22, and 23. And we also have 2 gas wells, 19 pipelines, and 2 compressors. Sorry. And so we have 3 cases here. The case 1 is a dynamic gas flow with power to hydrogen and methane and hydrogen effects. So this is a proposed model. Hydrogen effects mean that we capture all the dynamic flow characteristics in this case. And also C1 is a kind of a simplified approach where you only have a steady state gas flow. And then C2 is a dynamic gas flow with hydrogen effects, but there's no P2HM. Okay, so those are the numbers you can see after you run the simulation on this HB case. So you can see that we have basically we can see those congruent. So given this predefined threshold, which means that you have this threshold here. So basically, if you are if those variance in terms of energies or in terms of those reliability indices is less than this threshold, you'll stop. So given all the threshold that you can define, all the models can converge within certain iterations. And then the best reliability performance is observed in the proposed model, which is C0, because it captures the most, it provides the most accurate picture of this hydrogen flow. The worst LOMP, LOGP, and EDNS and EGNS occur in C1. The worst ORP and ERNS occur in C2. So you can see, you cannot draw a kind of universal conclusion. It's pretty much case dependent. But the idea is that, so even though you cannot have this common conclusion, you should still run the model, right? Because the model gives you different results. You may get different insights by running the steady state model and the dynamic model. So that's the key point message here. So, and also this is the impact of a gas flow dynamics. You can see that this is a C3, dynamic gas flow with hydrogen effects, and the C4 is a steady state gas flow with hydrogen effects. So you can see that you have different results from this run. And hydrogen fractions have different impacts on reliability in those 2 cases. Again, you cannot have this universal conclusion, but you still need to have a better model if you can. And you can see C3, increasing hydrogen fraction improves LOIP and the EDRS, but reduce, but increase as LOIP and the EGNS. And in C4, the opposite trend happens. So which is something new here. I will skip this slide. Basically, the same thing. Okay, so for the second topic, I want to talk about this planning. This operation, optimal operation of integrating energy system with hydrogen. So here we are basically looking at a more complicated scenario. We have hydrogen, we have heat, we have methane here. So renewable energy can produce electricity, and we can have H2 hydrogen here. You also have this heat supply here. Okay, you have water circulation system. Water can be heated and provide heat to the district heating system here. That's another benefit. And then hydrogen can also be blended into a natural gas system here. Hydrogen can be also consumed by hydrogen consumers directly here. Okay, so those are the technical constraints that we have. So this is the feasible region of power to heat and hydrogen here. So you have this complex combination, so you can describe this feasible region using those constraints here. We also have this electrolyzer temperature constant here, unique minimum here, because electrolyzer operates it's pretty much like a conventional generation units. It can be on, can be off, it can be idle, and we can model that through those equations here. We have all the hydrogen utilization equations here, power to hydrogen, hydrogen storage equations, hydrogen consumption, hydrogen to methane equations, and all those equations. And also we monitor this because you also involve heat here. So we learned from this paper you can actually model this heat transfer process here using using this change of electrolyzer temperature and heat loss. So then in that case you capture this heat modeling here also in this combined model. So this overall objective function here. So to make the problem more interesting, we also model this uncertainty from wind and solar. So we have this robust optimization model that can capture the worst scenario cost, load shedding that you have here. So those are the constraints that we have here. This is a conversion constraint. We all have this power distribution network constraint here, natural gas network constraint here. We have a heat network constraint here. Again, we run the model. In this case, the model is even more complicated because we add heat into the overall picture. So you can see the heat network. We have 3 electrical boilers are installed in nodes 1, node 31, and node 32 here. So you can see this is the system layout. Again, we run different cases. So you can see we have different cases. Steady state gas flow without hydrogen effects, and steady gas flow with hydrogen effects. Dynamic gas flow without hydrogen effects, dynamic gas flow with hydrogen effects. So we run a large number of scenarios, a large number of cases to see that how hydrogen affects the operation of integrated energy system. What's the impact of doing that? So you can see that total operation cost is going to be reduced because you have hydrogen. The source of that hydrogen is from wind and solar, which is free. So the overall cost is going to be lower when you have hydrogen in the system. And the steady state, which is a simplified version of the gas flow, as I mentioned earlier, can lead to inaccurate dispatch results. So neglecting the physical properties of hydrogen can misestimate the dispatchability of our natural gas system. So you don't want to do that. So last topic is the optimal planning of integrated energy system with hydrogen hubs. So this is the idea actually comes from Europe. So some researchers in Europe, they have been looking at energy hub for a relatively long period of time. So basically the idea is that you have different sources of energy. When you combine them into a hub, how to model that? How you can do your planning and operation with that hydrogen hub, with an energy hub. But in the past, they did not quite consider this hydrogen in the picture. So here we want to consider the hydrogen in the picture too. So then you have this energy hub model that we will have here. So basically, you have this electrical buses here. You have power grid, renewable energy, and electrical demand. And this can be coupled with the hydrogen hub you have here. Hydrogen hub, you have electrolyzer can consume power, right? And also, if the hydrogen is provided to fuel cell, it can generate power. So, and all this hydrogen hub is also connected with natural gas, because as I mentioned, the hydrogen can be blended into the gas system here. It also can be used to generate the synthetic gas through this methylation process here. And also, hydrogen can be stored in a tank, and it can be transported as well. Then for the natural gas, you have natural gas consumers also here. So those are the kind of constraints we have for the hydrogen model. Here we consider this combined concentrated solar power plant, CSPP. Also we have considered this high temperature electrolyzer model here, HTE. This electrolyzer model has a higher efficiency compared with the low temperature one. So, and then they have a new equations, new constraint, as I'm showing here. So these are all the kind of overall list of constraints that we can have in this model. So we have steam methane reformer constraint here, or hydrogen storage constraint here. We have SOC, state of charge, constraint for those storage capabilities. And then we have low temperature electrolyzers here, as you can see here. In comparison, we have a high temperature. Where is that? It's also in here, I believe, somewhere. I have high temperature electrolyzer constraint here. And so those are the conversion constraint. Hydrogen pipeline, hydrogen to electricity, hydrogen balance constraint. And here, because we are looking at investment planning problem, so we want to look at what's the minimum investment cost that you can achieve. So you can see we include the generator and the line investment cost, and all the SMR related costs, and the electrolyzer investment cost, hydrogen storage pipeline investment cost. So we are looking at multiple years in the future. So we also consider the operation cost, because when you have those investment decisions made, you still need to simulate how those decisions are going to work in the operation scenario. So you need to calculate the cost over a day or hour for the entire year. So this is the operation cost that you can calculate here. So we have generation operation cost and power shedding cost. We have energy hydrogen storage operation cost, and all those costs included here. So, and also the candidates, the investment decision can have multiple candidates. So they vary by location, by size, and by type. So here you can see that we have investment decision associated with the generator types and sizes and the location. And also we have electrolyzer investment decision here. We have low temperature, high temperature, and fuel cell. And also you have this investment decision for storage and pipelines. So this is the overall optimization formulation. So you have investment cost, which is long-term decision-making cost, and then you have short-term operation cost. So, and then we also have a multiple scenario to capture this variability in terms of solar and wind. So the planning decision is going to be related to location, size, and the type of your technology. And also it's going to subject to a certain investment budget here. And those are the operational constraints. You have the CSPP-based high temperature electrolyzer constraint, as I mentioned earlier. You have this hydrogen hub constraint. You have power system constraint. You have natural gas system constraint too. Okay, so we ran the problem in a 24-bus case, and then we have power system, hydrogen hub, natural gas, and you can see this is a mostly complete system that we can have here. So, and we ran a large number of scenarios again. So we have different scenarios, A1, A2, and A3. A1 is the proposed stochastic programming-based planning model. And A2, we only consider low temperature electrolyzers. Case 3, we have some uncoordinated planning model without electrolyzers and fuel cells. So then we can see that A1 has the least total cost, which is our proposed model here, as you can see here. So A1 is the A1 operating cost, the A1 total cost. You can see A1 total cost is smaller than A2 and A3 here. And also those are the decisions associated with the technology that we want to invest in. So those are SMR, and this high temperature electrolyzer, low temperature fuel cell, and storage pipelines. You can see all those investment decisions that are being made here. And A1 has the lowest total investment cost, total operational cost. And also the A2, when you only consider low temperature electrolyzers, so that increased the total operation total cost by 43.74 million, because the efficiency of low temperature electrolyzers is not as good as the temperature ones, high temperature ones. And A3 has the highest total cost. And you can see that 38% of wind energy is curtailed, which is really significant. And electrolyzers can help power consumption to absorb some renewable energy supply, because electrolyzers, they can be easily start up and shut down, so they can change their operation condition very quickly. So they are very flexible. So in that sense, they can help the overall system to absorb more wind and solar. And the fuel cell can also provide additional electricity, because fuel cell, if you supply that with hydrogen, it can provide, it can work as a battery. It can work as a generation plant when needed. And then we want to verify the model a little bit further. So we want to have a different operation modeling for those electrolyzers. You have this, we only model the those electrolyzers with one state on. B2 case, we have 2 states here, on and off. B3, we have 3 states, on, off, and standby. So then we have low temperature, and then we have high temperature. In the case H, we have both electrolyzer technologies here. So if you look at all the different cases, you can see that the proposed model can reduce the total cost while being consistent with practical operations. So you can see among all those cases, this case, the HB1 has a better case. And also the HTE, the high temperature electrolyzer, can help reduce the overall cost, because again, the efficiency of this technology is much better. So we also look at this computational performance of our model to see that if this can be run on a larger scale. So in this case, we kind of tripled the system that we just showed. So we have this system, we have 72 bus power system, 40 node natural gas system, and 8 hydrogen hubs. So this is the bigger system. So again, so we can have similar conclusions here. And we can see that we can still see that the C1, the proposed model, has the least total cost. And C2 and C3 can increase the total cost by $75 million and $436 million. Amount of curtailed wind energy in C3 is about 24% here. So you can see that even though the C1 takes most time to run, but it's worth doing that, because you can see the C1 has the least total cost. Another reason you can take a longer time is that it's a planning model. It's not an operational model. So a planning model, you don't have to get the result in one day. I mean, in several hours. It gives you more time to run. So that's the reason that we are not really worried about this computational performance here. But in the end, it still can be results can still be obtained within reasonable amount of time. A few hours in our case. So the conclusion is that you can see that I introduced this how we think that the hydrogen can be modeled and introduced into energy system. And we look at the 3 different aspects here. This reliability assessment, optimal operation, and optimal planning. So we look at the different technologies, different conversion processes here. Hydrogen to heat, hydrogen to methane, hydrogen coupled with concentrated power plant, solar power plants, and the different electrolyzer technologies. So in the end, the takeaway from our work showing here is that hydrogen is still relatively new, and there's a lot more work that needs to be done. And here we are just trying to introduce this topic to you guys, so that we can see that if you want to tackle the modeling aspect of hydrogen combined energy system, how can you do this? This is our way, our idea of doing this, and I'm sure there's a lot more that can be done. So basically, we can see that if you want to model hydrogen more accurately, you need to capture the dynamic gas flow in the gas pipelines. So when you combine, you blend hydrogen and gas, it's going to have an impact on the system reliability, on the system gas flows. So you need to capture that. And also, when you throw hydrogen into the overall energy mix, it's going to have this coupling effect with the other infrastructures as well, with heat, with the gas, with other. Also, it's consuming a lot of water too. So you need to consider water in this scenario as well. So in the end, it's a really complex problem. So I just want to show some kind of preliminary results that we are showing here. And I hope you'll become interested in this topic, and you can do more in the future. That's all I have. Thank you.
Thank you, Dr. Wang. The floor is now open for questions.
Thank you very much for the talk. I have just two quick questions. The first one is about what is the time step of the model that you're
Hourly.
Hourly. Okay, I see. And then the second thing you mentioned, there's a weighted operation cost. So what type of weight do you put in?
Because if you have this wind power curtailment, gas load and the power load, you're going to increase the cost. A penalty. So a penalty is you can assign certain, like let's say, $10,000 per megawatt hour. So you can assign this penalty into the object function. So in the end, you want to minimize that penalty. So that's weight is human made. Yeah.
Okay, thank you so much.
More questions?
Thank you very much
Yeah.
for the nice presentation. I have a question for the planning model. It's very interesting that you introduced unit commitment decisions. For the electrolyzer, how flexible or inflexible is the production of hydrogen?
It's very flexible. And because as I mentioned, so they can change their operation condition on, off, idle very quickly. So which means that it's like a fast ramping generation unit, like a gas turbine, a combined cycle, right? So you can change it very quickly. So it's not like a conventional power plant, a coal, not to mention a nuclear power plants. They don't change, right? So if they're on, they are on. For those high temperature and low temperature electrolyzers, so they can change their on and off conditions very quickly. So that's provide additional flexibility into the system operation. So that's the reason that we want to capture that. So that's when we model that.
Right. And in your opinion, how is this introduction to hydrogen into power system, into this or integrated electricity and gas pipelines going to happen? Are we going to start with these small trucks, for example, or these small pipelines, or how should countries approach this decision, or build big pipelines right away where potential hubs are?
I think it's happening now. As I mentioned, so some other places like Asia and Australia and Europe, they are moving ahead quickly. In the U.S., I think we have been working on that. If you see the news, the U.S. just invested this hydrogen hubs. It's $1 billion per hub. We have 7 or 8 hubs in the U.S. So it's happening now. And people in Europe are talking about this intercontinental pipelines. So it's happening now. So different countries have different methods, different ways of doing that, right? So Kanka may have some questions. So I'm not sure about how Canada is doing this, but it really depends on how much resources you have, right? How much hydrogen renewable you have. Because if you want to burn coal to produce hydrogen, it's not a good idea. So how much wind and solar you have, how much surplus you have, right? Wind and solar, and what's the existing infrastructure you already have in place. So it all depends. So that's the reason different countries are taking different methods. Okay. Did you want to add anything, Kanka?
We have a question online.
So-
Then we'll go over that.
Okay.
Sorry. We have a question online from Sharam. Sharam was wondering about what's the life expectancy of electrolyzer system.
Oh, that I don't know. I don't know that number. But this technology is moving very quickly. In my view, hydrogen by itself, it's pretty much like a solar power 10 years ago. So when you talk about solar power 10 years ago, it was like a hydrogen now. Because people think solar power has too much cost, it's not really realistic. But if you look at solar power now, it's everywhere, right? So I think going into the future, when more money is put into the research in terms of this hydrogen, the lifespan of those electrolyzers and the efficiency are going to get higher, get longer. So I think if we work hard on this as a group, I think we can achieve something much bigger. Yeah,
This is not a question, this is a comment.
Okay.
So Anshul was the PhD candidate. So he actually has carried out, you're mentioning that transatlantic hydrogen transportation. So he has actually carried
Yeah.
out work on that Canada, Germany hydrogen contract and agreement, which is recently MOU has been signed. So he has developed a planning model for that, and probably Anshul can make a brief comment on that, what you've done.
So that was a planning model based on the MOU which was signed in March 2024 between NRCan, which is Natural Resources of Canada, and the European Commission, mainly in Germany, which will be transporting from Newfoundland, generating from wind, to the green hydrogen generating from wind from Newfoundland province in Canada to Hamburg in Germany. So the model which we developed was a planning problem where we consider the life expectancy of electrolyzer based on current data to 5 to 7 years, and for fuel cells. So in that planning model, we did the capacity planning for amount of electrolyzers which would be needed and the amount of wind power plants which needs to be installed to meet the contracted demand of how much million tons have been already contracted. Also, in that study we performed the sensitivity analysis of at what price they should be selling, and also the economic analysis of net present value and the IRR for the project.
Yeah.
Questions?
Thank you for the nice presentation. One of the projects we're working on right now is looking at the feasibility of the hydrogen or fuel cells for remote communities in Canada. Just wanted to see if you've done any work in that regard, or because our preliminary research shows they are promising, it can be viable, but just wondering from your point of view, like extreme cold conditions, for example, how it impacts the hydrogen systems and their production and so on.
Yeah, I have not looked into that myself, but that's the last topic. That's a hydrogen. That's a hub concept. It can be applied there, I think, because it's remote. It's an isolated system, right? So you may have the requirements in the demand for heat, for power, and all others. So if you have this energy hub, hydrogen hub, put in the remote village, like a microgrid system, right? So that may work well. So in that case, you have this integrated energy system. You not only satisfy the power demand, you also satisfy heat and other demands. So I think that the energy hub may play well there.
I assure you Dr. Wang will be here for the next 5 to 10 minutes if you would like to have some kind of networking with him on a face-to-face basis. Dr. Wang, on behalf of the Waterloo Institute for Sustainable Energy, Department of Electrical and Computer Engineering, Management Science and Engineering, University of Waterloo, and the entire audience, we would like to thank you for your time and for your great presentation. So kind of you, sir. Thank you so much.